Welcome everyone, and this is going to be our last instructional video series for the fall semester of UmpTump Calc 1. In this class, we are going to look at optimization. Historically, we've touched on Newton's method. However, you're going to have a winter assignment that is going to touch on that. So we're going to leave that for the videos and your winter assignment. So with that being said, there is going to be a winter break assignment. There are actually going to be two different pieces to that. So just know that each piece it'll have its own video series, and you'll have some paperwork to do and then some web work as well. Okay. The other announcement is that we are going to have our last exam coming up on the 17th. More information will be shared about that and the review session in class this week. Okay. But optimization comes into play when we talk about maxima and minima. In the last class, we just spoke about finding maximum and minimum of a function using the first and second derivative tests, and particularly using those to verify that the critical numbers create a local min or a local max. And then we also talked about absolute mins and maxes. But not all maxes and mins are restricted to a graph, right? We can find a maximum and minimum of a function from a particular context. And this sort of exercise you've seen back in math analysis and in algebra. It's one of the classic examples of optimization. We are going to look at something a little bit different than this, but nevertheless, the idea here is the same, that we want to find the dimensions of the pen that create maximal area. Okay, so what we generally did in math analysis and algebra is we said, okay, here's a river and here's the pen that we want to create that borders the river. Okay, we don't know what dimensions it has, but we say its dimensions are x, y, and x because it is a rectangle. Okay, and then we said, we have 2x plus y is equal to 500. That's the perimeter. That's the total amount of fencing we would have to use. But then the area, right, is x, y. And what we would do is isolate y here. So we have 500 is minus 2x is equal to y. Substitute that in to the area function. And so we get 500x minus 2x squared, right? And then this is a quadratic function. This is technically a of x. And so then I can find the value of x that produces the maximal area to be at the vertex. So that would be minus b, so minus 500 over 2a. And so then what is that, 500 over 4? So 125. And then consequently we find that y is 250. Okay, so then I would just have to say that we have the two widths should be 100 or 125 feet and the length should be 250 feet, and I would write that all in a sentence and I'd be done. Now here, when we found the dimensions, right, we made use of the properties related to this quadratic function, right? We know it's a quadratic function and there is precisely one min or max. Here in this function, right, it is a parabola that the graph of this function is a parabola that opens down, so the vertex is going to be the maximum, which is what I did to find the value of x, as I located the x value of the vertex. Okay, so that's the idea that we're going to be using here. As we go forward, we are going to be, setting up a diagram, writing an auxiliary equation, finding a function that we are to maximize, and then finding the maximum or minimum value. We will have an additional task of verifying that these are maxima and minima, and that will come through the use of calculus and our first and second derivative tests. Okay, but this is the idea that we're going to be using in this class. So let's see how it gets modified.